So, hello everyone and welcome in this presentation about the usage of KLEE in the tool Lazard. I am Etienne Boespflug, PhD student, and this is a joint work with Christian Henné, Laurent Mounier and Marie-Laure Potet, all from the Verimag laboratory at the University of Grenoble. In the first time, I will introduce the context of this work, that is fault injection attacks. Then I will describe the tool Lazard and especially the interaction with KLEE, and finally I will conclude and present the future works. So physical attacks are usually regrouped in two main classes: side channel attacks study physical information such as power, execution time and such to find secret data about the program. On the other side, fault injection attacks are more intrusive and use physical processes to induce faulty behaviors in the target program. Those processes include laser attacks, power and clock glitches, or electromagnetic pulses, for instance. Many effects can be induced by faults. Common effects include instruction replacement by modifying the opcode, changing the value of the operand in the instruction or in the data in the registers and the memory. And faults can even lead to effects that are not defined in the instruction sets when architecture-specific parts of the component are targeted. For instance, hidden register. At software level, which is the one that we focus on, it can be translated by control flow and data flow alteration, and more generally, modification of the invariant of the program. That is, standard analysis tools cannot be trivially applied to this kind of attacks. So on this slide, you can see a typical example of PIN code verification program. The user PIN is compared against the secret one in byte array compare function. The program uses a try-counter GPTC, and we represent authentication with the global variable G-authenticated. The program is correct, but if you consider the possibility to inject faults, then several attack paths become possible. This depends on the fault model and the attack objectives. Here we consider that the opponent wants to be authenticated using a false PIN code. And on the right, you have an example of main function of an analysis test case with the tool Lazard. The attack scenario is expressed with KLEE-Assume. And line 10 and 11 show an example of protection against runtime fault injection. The number of loop iterations should be equal to the pin size. For this example, if you allow up to 4 fault injections, Lazar produces the result shown in the table below. Here we use a test inversion model, which allows the opponent to invert the result of a conditional branchment at the execution time. The figure on the right presents the control flow graph of a two-fault attack, consisting in inverting the byte array compare loop and to bypass the loop counter verification. Here. So you can see that the last fault inversion concerns the protection itself, because in multiple fault contexts, the countermeasures themselves can be attacked. So Lazar is a code analysis tool working on the LLVM intermediate representation and using dynamic symbolic execution with KLEE. Its goal is to evaluate programs in the context of multiple fault injection to assist developers and auditors. And the figure shows the general workflow of the tool, which take as input the program, the attack objectives, and the fault model. The program is compiled and then mutated in order to take into account all the possible faults. And then the mutated bytecode is given to KLEE, which generates a set of faulty execution paths. And in a later step, we parse KLEE results and perform several analyses on this set of traces. So the first step is to generate a mutant from the compiled source program, which includes all the possible faults. Symbolic Boolean variables determines if a fault should be injected, and mutation functions are called on each instruction that is faultable depending on the specified fault model. Lazards support different fault models, which the main one are test inversion and data modification. And after this mutation pass, the higher order mutant is provided to KLEE. On this slide, you can see an example of mutation function for data fault injection. At line 4, there is a first symbolic variable that is used as a boolean determining if a fault should be injected. If no injection is made, the original value is passed as parameter. The original value passed as parameter is returned. And in the case of fault, if the total fault count is lower than the user-defined fault limit, another symbolic variable is used for the value. This value can be optionally constrained by a predicate specified by the user, and the total fault count is incremented. And the fault is logged on the standard output for later processing. Here you have a small example of bytecode including test inversion and data fault. The original bytecode is on the left and the mutated one on the right. The data injection in red is made on the load instruction lane 2 of the original bytecode, and the test inversion fault in green is made on the branch instruction at the line 6. For each fault, we use the corresponding mutation function here and here to simulate the fault. And there is some other computation. For instance, in case of data fault, we should technically modify all usage of the mutated temporary. So instead, we allocate another variable, which should be in red, in fact, and this temporary is used in the original load here to avoid to have to propagate all usage of the variable. So after KLEE execution, traces have to be gathered by the tool. The mutant bytecode is instrumented with printf to log the different events in the trace. It includes the Boespflug traversed, the fault injected, and some other events such as countermeasure triggered, for instance. Then we parse KLEE's replay tool, its output for each k-test, gathering the event in the trace. The figure on the right presents the control flow graph of the two-fault attack on verilyPIN with test inversion model, and the figure below shows the attack printed in Lazard, which includes the execution path with the two fault. Each trace is associated with the type of termination which is provided by KLEE, and in this case the trace is correct, meaning that the attack was successful, but it could also be an execution error or failed assertion, for instance. Laser objectives are expressed with KLEE-Assume encapsulated in the macro, but it's not very important in your case, and the fault model and fault injection space, meaning the set of source location in which the fault model apply, are defined in a mutation strategy file that is presented on the right. And optionally, you can achieve finer granularity for the model with source instrumentation. Laser also provide other features such as the Python API for manipulation of analysis, attack traces, and some utility function to generate analysis reports or attack graphs. It can also apply automatically some countermeasures such as test duplication or a simplified version of SecSwift, and implement countermeasure optimization methodologies that has been published at FDTC 20. So in conclusion, we use mutation function to minimize the impact of the mutation phase on the code structure. This also allows to extend easily the tool with more false models because you have to write your model in C instead of LLVM. And using dynamic symbolic execution with KLEE gives realistic analysis time, even for multiple fault injection. And finally, the tool has been used in real-world contexts, such as in the Wookie bootloader in the STIC 2020. As future works, we plan to implement quantitative analysis, that is, being able to count how many attacks are associated with a symbolic attack. And we also plan to extend our analysis of countermeasures. Thanks for watching.